Already have discussed the introduction of the analog circuits. How VLSI started, why VLSI is important, and why VLSI is generally used. So I've said that VLSI have started in recent days. So it's not very recent. It started in say 1970s, somewhere in 1917. So even if I say something very recent, it's not like started in few years. It started in 1970s sometime. And then I also have said the technologies that are used in analog circuits like bipolar junction transistor and CMOS. So apart from this, there are some other technologies like BiCMOS, which are also used for analog circuits. But mostly these two are the one. And then I have said the market, what are the different commercial aspect of analog circuits, where they are used, and the requirements. Requirements, especially these requirements are in say input output systems. Okay, so these are the requirements of analog circuits. And what is custom design? And I also have said what are the different trade-offs. Multi-dimensional trade-off means you want to adjust the speed, but at the same time, if you want a high speed, you may lose something else. Say you increase the speed and you found that the bandwidth has been reduced. So it's not like that you only use one particular parameter and enhance it. You will find that the consequence is somewhere else. Once you make something better, something else is getting worse. So this is multidimensional trade-off. You have to take care of all this. Now the next I would like to discuss is why analog electronics. So far I said why analog electronics from market perspective. Analog electronics is required in so and so applications. But technology wise, why we should use analog electronics? That is also an important question. So if you go through the book Razavi, which I have suggested in the list of reference books or textbooks, it starts with the introduction. It starts with this statement in the introduction part. Generally we skip the introduction part, but they are really interesting. So when digital circuits came in to the picture of entire electronics in around 1980s, then they predicted that analog circuit will be vanished from electronics. There will be no requirement of analog circuits in say next 5 years or 10 years. In 1980s, they said. But as technology progressed, they found that they cannot get rid of analog electronics, especially after 2000. Because whatever we see in the nature is a function of time. And whatever is a continuous function of time is analog. So most of the signals, in fact all the signals, I am not saying all because considering the limitation of my knowledge, probably I don't know everything, but most of them, I would say 99%, I'm just keeping 1%, actually it's everything, but still I'm saying even if something is there, it's very rare, but most of them are analog. Whatever we see in the nature, whatever signal we get from the nature, say the voice signal that is coming, it's actually analog in nature. Then it is received by the microphone, then we process it in digital domain after converting this analog signal into digital. So you need an analog front end to receive this signal. Whatever analog signal you are getting from the nature, you need to at least receive them using an analog circuit. So you cannot ever get rid of analog circuits. In fact, people found in around 2000 or after 2000 that analog circuit design is a very crucial part of any circuit analysis, because this is, as I said, this is custom design. It's kind of for each system you need a separate circuit. You cannot use the same circuit for everything. So analog circuit is a very special kind of design. So that is why you cannot get rid of analog circuits ever. Now this is the basic system that has been shown here. Okay, so you have an analog signal, and when you have an analog signal, you process it through an analog to digital converter. ADC means analog to digital converter. Analog to digital converter. Okay, which is known as ADC. Similarly, we have digital to analog converter as well, because the requirement is you take analog signal, you convert it to digital, process it, then again convert the digital to analog for visualization or something. In many of the cases, you need a DAC as well at the output side. Okay, but this thing is almost necessary in most of the circuits, wherein you get an analog signal first, you pass it through an ADC and you get digital data. It's just a representation. Okay, and then you do digital signal processing using any digital signal processor. Okay, so this is the basic structure. However, in practice you'll find that actually the signal that you are getting requires amplification, then filtering. You'll find there are a lot of noise signals. You need to filter those signals before you process it. So you have a signal, then you pass it through an amplifier which will further amplify the signal, and then you filter it to reduce the noise, whatever unnecessary signals are there. Then you pass it through an ADC, then you do a digital signal processing of the same. So this is the complete, more or less the complete block diagram of a system. It's a generalized system. Okay, just in general we are discussing. So this is why we need analog electronics. So you cannot get rid of analog electronics. So there are some examples. For example, say digital communication. In digital communication, if you have a lossy cable, say which is made of some metal, copper or something, and you have a V in as an input, you are getting V out as an output. Now in input side, you have a digital signal. Digital signal means you have only two stage. This is 0, or sorry. So this is 1 and this part is 0. So you have a digital signal which is in the input, and then you pass it through a lossy cable and you find out an output which is of this shape. So if you look at the output, probably the time periods are same, but it more or less like an analog signal. You cannot process this kind of signal using any digital signal processor. It's not a very good output signal, because most of the things, because this medium is lossy, you lost few of the signals. So at the end you found this type of signals. So you need again an analog circuit to process this. Then there is another example of which is known as multi-level data. Generally we use digital data which is binary. I already have shown 1 and 0, but there is a new concept that is coming up which is multi-level. I mean, they are using different labels which helps in sending datas in a lot of datas together. So this is a new concept wherein you have different labels. Other than 2, you have, say here it is a 4 level data. You can see that this is one level, this is one level, this is one level, and this is one level. So you have 4 different levels. So you have 4 levels data or multi-level data. So this is another example. So, but you need, in this case, you need analog circuits to process this kind of data. Okay. Sorry. There is another example, which is the storage disk. That is the hard disk that you use of, say, 500 GB, 1 TB hard disk nowadays you get. Now when you store the data, it's in the form of digital like this. But mostly what happens when you retrieve the data, you want to get back the data in an high speed memory devices, you receive an output of this sort, which is more or less what I have shown in the previous slide, where the noise level is as high as 2 millivolts, which means that you need to retrieve or recover data from this output signal. You cannot use this signal, probably you'll lose a lot of data. It's not a very distinct signal. So you need a recovery to recover data from this output signal. So in this case also you need analog circuits. So nowadays, these drives are so important. If you get 500 GB, it's not sufficient. You need 1 TB. Memory is generally a big requirement, and people also want high speed memory devices. So high speed memory devices, this type of things are usually you will find this type of things. So you need proper recovery circuit so that you get back your data, whatever you've stored, you can get back those data. Okay. Then in wireless communication system, I said that wireless communication is a big market for analog circuits. It has a front end. Now, one of the major problem in this wireless communication system is if your circuit is not linear properly. If it's a non-linear circuit, you'll find different interferers. So this is the frequency which you want, but you get different interferers. Interferers means unwanted frequency signals. Sometimes they can be, the harmonics, but you don't want them. But if they are very close, there is a huge chance that you will not receive the proper signal. So there are different circuits like frequency booster. So what booster will do? It will increase the desired signal, and this signal will be always high than interferers, which is one way of doing this. Another way is you just shift those interferers far away. Say here you have interferers and here you have desired signal. Okay, so if they are far away, so they will not be creating any problems as such. Okay, so in wireless communication system also you need analog circuits. Apart from this, there is another thing called optical receiver system. What is optical receiver system? I already have once discussed in the introduction part that you have an optical fiber, but in the both ends you have a receiver, you have a transmitter. So you have a laser diode in this side, you have a photodiode at that side. So this is receiver. Photodiode is receiving whatever signal is coming from the laser through optical fiber. So in these cases, the receiver is receiving an analog signal. So you need an analog front end. Then whatever is received from here, then you convert it, as I have shown previously also, amplifier, then maybe filter. You filter it and then you put it to analog to digital ADC, analog to digital converter, and then you have DSP. Okay, so that way it works. So in optical receiving system also you need analog circuits. And then you have sensor system. Now sensor is a very buzzword nowadays. Everywhere you'll find there are a lot of sensors. If you take the recent days mobile devices, you'll find they have a lot of sensors embedded into the smartphones. One of the major technology in this sensor is MEMS devices. Okay, MEMS means micro electromechanical systems. So these MEMS technology, micro electromechanical systems, are used for, say, accelerometer, gyroscopes, which is there in your mobile. Accelerometer is there in your mobile. Now here in this slide I've shown one example. It's not necessarily that all accelerometers are of this kind. There are different types of accelerometers, but in this kind, in this type of arrangement, it's mostly capacitive. Capacitive means the capacitance of the sensor will be the sensing parameter. So say you have a fixed plate, which is shown here, and you have a deflectable plate. Now when in motion, this deflectable plate deflects from one side to the other. Now when it comes closer to the fixed plate, this capacitance between these two plates will, when it comes closer, it will increase. Why? And when it goes away from this, it will decrease, isn't it? So based on this capacitance, you'll get to know what is the acceleration. So they have modified the structure in here, wherein they have used two capacitors in series, say, and they can get a more sensitivity out of it. So it's kind of a cantilever structure. So cantilever structure is very common in MEMS. So you can use this kind of structure for sensor systems. So there are other sensor systems as well where analog circuits are required. This type of variation, all these things are analog. So you generally need an analog front end for processing this kind of sensor data. Okay. So this is one example. Now this is basic capacitor concept. When it comes closer, the capacitance will change because it depends on the distance between these two. So I already said that why it is changing. It's a capacitance is a function of distance between these two plates. So once the distance is changing, your capacitance will also change, will also vary. So next is different other applications like biomedical, which is also very important. So different biomedical application also requires different kind of sensors. So ultimately you need analog circuits to process them. So there are few examples given, say blood clotting measurement sensor or device, which require analog circuit. And then you have different ECG, EMG, electrocardiogram, electromyography. These things also require analog circuits. Then you have robotics and implant surgery, very, very new concept. So in each of them you need sensors. So wherever there is a sensor, you need an analog circuit. Then you have biosensors. Now these type of systems are little complicated because in biosensors you will be using microfluidics, you may use liquid system, and in this case you need to take care of the noise. So these things are little complicated, but anyways, whatever it is, you need to use an analog circuit to process the signal. Then the sensor interfacing is, I already said, the front end circuit that you need. Signal conditioning means, say you need amplifier, you need filters. All these things require analog circuits. And in point of care devices, biosensors, they are more or less connected. Point of care devices mean on-site detection. You'll find nowadays you have glucometers, you have blood pressure monitoring, which can detect or which can give you results on site. If you have a patient, you have an electronic device which will tell you what is the blood pressure of that patient. Or if you have, say, you want to measure the enzyme, some of the enzyme level in blood, say amylase level, blood amylase level. So you have a device wherein you put the blood, it will say the blood amylase level. Blood amylase level is required to know whether a person has pancreatitis or not. Say blood sugar, which is now very common, AcuCheck. You have sensors and which is connected to a device. You have a display here, and in here you put the blood, drop of blood, and then it will give you what is the value of the blood sugar. So this type of point of care testing, that is on-site detection devices, require analog circuits. So these are some of the applications from application perspective I am saying. Okay. Now one of the important circuit for all these analog devices is the impedance measurement circuit. Many of the sensors are impedance based. I already said maybe they are resistive or capacitance change or something of that sort. So this is a basic impedance measurement circuit. So if you see the circuit closely, you will find there are different digital as well as different analog part. So if you look at it, you will find there are low pass filters, there are gain amplifiers, there are the amplifiers, and there are oscillators. So all these things are analog components, and you will also find different digital components for digital signal processing as well. So for example, this register, imaginary register, so these things are digital components. So you have analog and you have digital as well. So you cannot run this kind of sensor device or whatever wireless systems without analog circuit. So analog circuit will always be there, and it's now gaining a lot of attention because of this mixed signal analysis chips, ASIC, application specific integrated circuit development. The requirement of these analog circuits are high, very high. Okay, so demand is currently increasing. So this is a sensor system, just as an example, just to give you an idea that how sensor system is connected to analog circuit. So this sensor system has two electrodes, and it measures the impedance. So it's a kind of biosensor which detects kind of bacteria or something of that sort. I'm not going much into details of this paper, of this particular system. I'm just giving you an example, okay, how they are used. So this is your sensor system. Okay, now this sensor system requires a driving circuit. Ultimately, you will get a change in impedance, say in presence of a particular cell. So when this particular cell is there, you'll find that there is a change in impedance, and that change in impedance you measure using a impedance meter while you are developing the sensor. But you cannot bring an impedance meter everywhere with the sensor, which is a big device. So you need a readout circuitry. You need to convert the sensor concept and to a device. I mean device, when I say device here, it's kind of a point of care testing device, a small portable device kind of thing which people can use very easily. So you have to replace this measurement system using some analog circuitry. You may need to have a digital processor as well in order to process the signal that is coming from the sensor. You use microcontroller and different things, but you also need a portion of analog circuit, at least to amplify, to filter the signal that is coming out from the sensor. Now in this kind of biological system, you'll find there are a lot of noise, so you have to work little hard to make the circuit. Okay, for example, if it involves say fluid, you cannot use very high voltage, then it will start electrolyzing. High voltage, I mean you can't even go beyond say 1.5 volt or maybe 1.2 volt or something, where the liquid will start degenerating, so you'll get a lot of noise. So it's always a problem. maybe you are making an pH sensor, and if your circuit is not properly designed, and if it says that if you find that the voltage that is applied across the sensor may be more than 1.2 volt, you will find the liquid will degenerate and you will find a lot of noise signal. Maybe the pH level that is shown in your meter will be completely wrong. So it is a tricky job. You have to be very much careful while you are designing this kind of circuits for different sensors. Okay, so this is a typical sensor system. So the idea is analog circuit will be required for further years as well. It's not like that analog electronics is gone as digital has come up. So you always need a portion of your whole circuit as analog, because ultimately you need to process or receive the analog signal that is present in the nature.